Alrighty, so this lecture will be continuing our talk of Newton's laws, forces and accelerations, by incorporating friction. So, whereas in the past we've been doing problems with no air resistance, no friction, just nice, ideal theoretical circumstances, we're going to start implementing some more real-world stuff. Obviously, in the real world, when you kick a ball, let's say you kick a soccer ball on a soccer field, it'll roll for a while, but eventually slow down and stop because the grass has a lot of friction and it slows the ball down. Newton's first law would say, well, once you kick the ball, it has a certain velocity, and that velocity should remain constant unless there's an outside force. And of course, that's exactly what we see. The ball doesn't stay at constant velocity, it slows down. Thus, there must be an outside force, and that force is what we call friction. We all have experience with friction. We know what it is. It's when two surfaces rub against each other. That slows down the object. Now, how it does it, you could look at it microscopically and see, oh, well, the molecules of the two surfaces rub against each other. That makes the molecules vibrate and heat up. By vibrating and heat up, it's stealing energy that was used for motion to create heat. And so since energy is being lost to heat, instead of being used for its motion, it can slow down. But we're not really worried about exactly how physically friction works. What we want to know is, how do we incorporate friction into the types of problems we've been solving? So, in order to do it, the first thing you need to know is that friction will be a force. So I'll have the little variable F with a little f on the bottom, and that means frictional force. There are two types of frictional force. The first is called static, and the other is kinetic. What's the difference between these types of frictions? Well, it's basically in the name. Static friction is friction when the object is not in motion. So this is something like this. You have, let's say you have the refrigerator in your kitchen. You want to slide the refrigerator out from where it is. Maybe you need the dust behind it or whatever. Well, as you try to apply a force to the refrigerator to move it before it's in motion, there's a certain amount of force you have to push or pull before it'll start moving. Or a sofa. You want to push a sofa across the carpet. Well, you could apply a force and it won't move. It's just going to sit there. But eventually, if you push hard enough, then the sofa will start sliding. So, static friction is exactly that type of friction. It is the friction you must overcome to get something to start moving when it's not already moving. Kinetic, obviously, is the exact opposite. This is a friction on an object which is already in motion. So this is something like if you push hard enough on the sofa and you just push really hard, it'll slide away from you. As it's sliding away from you, when you're not touching it, it's going to slow down and stop. As it's sliding, there's friction between the carpet and the sofa, which is going to slow the motion until it stops. Same thing with anything. Let's say your car. The car is in motion. If the car, well, let's say the car is parked, the tires are on the road, the car is not moving, that's static friction. You have to push a certain amount to force the car to move. Let's say now the car is in motion, you're driving 60 miles per hour, and you slam on the brakes. Slam on the brakes, it locks the tires up, let's say, and you skid. Well, during the skid, the car is in motion. It's skidding along the road. Well, the friction between the tires and the road while it's skidding is kinetic friction. It's really easy to tell the difference. Static means you're not moving yet. Kinetic means you're already moving. Either way, there's friction involved. Why in the world do we have two different types of friction? Why don't we just say there's friction? Why is there kinetic and static? It turns out that in this universe, the amount of friction felt by an object is different for static versus kinetic friction. So it turns out static friction is higher. That is, there's more friction when you try to start something to move than when it's already moving. So kinetic has a lower frictional force. So this, again, if you think about a sofa, you're trying to slide the sofa across the floor. You have to push fairly hard to get it to start moving, but what you'll notice if you're very careful about analyzing what's going on, once it has started moving, it's actually kind of easy to keep it moving. It's like you don't actually have to push as hard once it's already sliding. And the reason is because the static friction, that is, the amount of friction you have to overcome to get the sofa to start moving, is higher than the kinetic. The kinetic being how much friction you feel as it's already sliding. So that's good to know as a conceptual thing. We won't deal too much with the difference between static and kinetic. As you progress into physics, if you progress into physics, of course, then we could start looking into when is static friction important and when is kinetic friction important. But for now, just leave it as a conceptual point to know that an object which is not in motion yet is harder to push than an object which is already in motion. All right, now the big boy. What is the equation which tells us how much force is there because of friction? The equation is actually very nice. Frictional force is equal to some number called mu. This is a Greek letter, mu. And what it is called the coefficient of friction. Basically what this number is how rough is the surface. This number almost always is something that would be given in the problem. You'd be told, oh, the coefficient of friction is 0.2 or something like that. And then the other is normal force. And we kind of introduced it in some previous videos, but for now, we're really going to look into how to calculate the normal force appropriately, because in order to calculate friction, you have to know what the normal force is. But that's it. You want to calculate frictional force, you multiply the coefficient of friction, mu, times the normal force. And that gives you friction. So, let's try an example. A nice basic example we had at the very beginning of Newton's laws. You have a flat horizontal table. There's a block sitting on a table whose mass is 10 kilograms. Let's say I push on the block to the right with a force of 100 newtons. And I will say the coefficient of friction for this problem mu is 0.2. Question says calculate the acceleration of the block. All right. So we want to handle this just like we did before. Let's make sure we know what are all the forces in this problem. Well, we have our applied force of 100 pointing to the right. Of course, there's always gravity. Gravity always pulls straight down, mg. And I also know there's a block sitting on the floor. The block's not moving through the floor, so the floor must be pushing up, preventing the block from moving downwards. So there's also some normal force. What else? Now we have friction. And the reason I know is because I have this little thing right here. That tells me friction is involved. If you're looking just at a picture of a problem and I want to show that there's friction, I would have this mu equals blah, blah, blah. If I'm giving you a word problem, then of course I'd say the coefficient of friction is whatever. But we know this problem has friction because of that yellow mu is sitting there. So since there's friction, there's one extra force. Friction is a force. Which way will friction point? Well, here's the rule. Friction always points against the motion of the object. So if you ever want to understand which direction friction is pointing, pretend that there's no friction. If there's no friction, which way is this box going to move? Well, obviously, looking at the box, the force is pushing it to the right, so the box wants to move to the right. Since I know the box is moving to the right, friction has to oppose it. So there's some frictional force which points to the left. So again, the direction of friction is very easy. If you know how the box wants to move without friction, then friction points in the opposite direction. Here the box wants to move to the right because I'm pushing it to the right, so friction must point to the left to try to stop me. All right, so there we go. Those are all the forces in my problem. Now I say, what's the question? Calculate the acceleration. Again, just like before, I asked the question. In which direction, what main direction will this block move? It's going to move in the x direction, left and right. So I'm going to look in the x direction. I'm going to use the equation. Sum of the forces in the x direction equals ma. And now all I have to do is look at my picture and plug in what are all the x forces in this problem. Well, I've got 100 to the right, and I've got friction to the left, so it's minus friction. The minus, remember, is not because it's friction. The minus is because it points to the left. Left is negative, right is positive. So, 100 to the right, friction to the left. Those are all the x forces in this problem. Remember, I'm not looking at any of the y stuff. That's equal to m, which is 10, times a. And there's my equation. Well, I want to solve this for a, but I can't. I can't do it because I don't know what is this frictional force. I don't know that. If that were a number, then I could solve the problem. But it's not a number. So I have to leave this alone for now. However, there's another direction I can look in. I need to know frictional force. What do I know about the frictional force? Well, I know frictional force, by the equation, is mu times the normal force. So if I could plug the numbers into this equation, that'll give me frictional force. That's now a number, and I can plug it into my main equation and get my A. So what are the numbers here? Well, mu, that's given in a problem, is 0.2. What about normal force? I don't know normal force. But can I calculate it? I can indeed. Which direction is normal force pointing? Normal force points in the y direction. So let me look in the y direction and use the sum of the forces in the y direction equals ma. What are all my y forces? Well, I've got minus mg down and plus normal forces pointing up equals the mass times the acceleration in the y direction. But how fast is the block moving up and down? He's not moving up and down. He's trying to fall through the table, but the table's pushing back up. They balance. So the y acceleration is just 0. All right, so now all I have to do is solve for normal force. Normal force equals, bring the mg to the other side, mg. Do I know what m is? Yep, it's 10. Do I know what g is? Yep, 9.8. There we go. I now know normal force. Once I know normal force, all I have to do is take that, plug it in right there. That'll give me my frictional force. So 0.2 times 98. What does that give me? 19.6. Now I know friction. Friction is 19.6. So take this, plug it in for my friction. 100 minus 19.6 equals 10 times A. So I want to solve for A. 100 minus 19.6 is 80.4 equals 10 times A. Divide by 10 on both sides, I get A is equal to 8.04. And there we go. This is how you solve a Newton's law problem when it involves friction. Notice this side over here is the same as all the other examples we've done. You have all the forces, you're looking for the acceleration. What's the direction of the acceleration for this problem? The x direction. So I look in the x direction and do F equals ma. Plug in all of my x forces in, and I solve for A. The difference is, one of my x forces, I don't know the number yet. That's friction. So I have to calculate it. But thankfully, the formula to calculate friction is easy. That's what this is over here. This right side is how to calculate friction. You start with the frictional force equation, mu times normal force. In order to calculate it, you need to know what the normal force is. Now, I went through multiple steps to calculate normal force, formally. But you're going to see, as you do more of these problems, you kind of get used to what the normal force should look like. And you can kind of fill it in without having to go through all the steps. You'll see that eventually. So, although this looks kind of like a long process, in actuality, after you've learned this, you'll see that the process is really only half as long. But anyway, how do I calculate friction? Mu times normal force. How do I calculate normal force? Well, look at it. Look at your picture. What direction does the normal force point? Here it points in the y direction. So do F equals ma in the y direction to calculate normal force. Here we know the A in the y direction has to be 0 because the block is only sliding in the x direction. So F equals ma is really F equals 0. Plug in all my yf's, my y forces. One of them is the normal force. Solve for normal force. I get a number. Once I have that number, plug that into my frictional force equation. I now have friction. Now that I have friction, go back to the beginning, the main equation for the problem, And now you can solve your question. Let's look at another example. Now that we've seen one in practice, let's do another. Example 2. Another flat horizontal table with a block of mass 10 kilograms. Now I've got a force F1 of 100 to the right, and I've got another force F2 of 20 pointing down and to the left at an angle of 30 degrees. Given the coefficient of friction is 0.2, I'd like to calculate the acceleration. So I want to go through this, and I want to do it in very high detail, more detail than I would normally go about solving this problem, because I want you to see, all the high-level steps that are done. And even though, in general, once you're used to solving these problems, you may not do it this way anymore because it takes a little longer to do it, it'll be more helpful, and it'll be better for you to see how these things are coming up. So what I mean by that is, let's look at the block by itself. And let's look at all the forces that are acting on this block. Okay, this is basically going to be a free body diagram. So that means you have the object. What are all the forces acting on the object? Okay. Well, let's say we have the force of 100, F1, going to the right. F2 is like this. What else? Are there any other forces? Well, sure. Gravity pulls down, Fg. And we know, since this object is on this surface, and gravity is pulling it down, but the object doesn't fall through the surface, there's a normal force. And the normal force is, by the definition of what normal means, if you remember from a few videos ago, normal means perpendicular. So the direction of the normal force is always perpendicular to the surface. Here, the surface is x-directional, it's horizontal, so the normal force must be vertical. And of course, the direction that it points in is preventing you from falling through the floor. Thus, the normal force must be up. Normal force. So those are all the forces. Oh no, there's one more force, I'm sorry. There's also friction in this problem. Because of that yellow mu equals 0.2, that tells us there's friction here. So we want to figure out which way would friction point. Now sometimes you can't figure it out. Sometimes there are so many forces involved, you don't know which way wins out. If that's the case, just guess. And what would happen is you would just get a negative answer somewhere. Okay? Here, however, and for almost every problem you have, you'll be fine. You'll know how to figure it out. For instance, look at this problem. What are the forces which are going to move this object if I don't think about friction? Well, let's see. I've got 100 pushing to the right, and I've got 20 pushing down and to the left. This down and to the left thing means not all 20 is to the left, because some of it is downward. So it's something less than 20 is pointing to the left. Well, if I have 100 to the right and something less than 20 to the left, obviously the force to the right is bigger, so my block wants to move to the right. Thus, I know if there's no friction, my block will move to the right. However, if there is friction, if my block wants to move to the right, friction stops it. So friction points to the left, in this case. If, however, the F2 were bigger, and there was more force pushing to the left, then the block would want to move to the left, so friction would have to point to the right. For the problems we're going to work on, you'll be fine. If there's a problem where we can't figure it out, I'll show you the steps to go through. You have to do a little math, so it's a little tedious, but I promise the problems we're going to worry about, you'll be able to look at the information and pretty much tell which way is the correct way. The big rule is friction always points in opposition, the other way, to the motion. Here my block wants to move to the right, so friction pushes to the left. All right, the next thing you say is, okay, which way does my block want to move? It wants to move in the x direction. So that means x and y forces are important. Okay? Unfortunately, F2 is an angled force. F2 is sitting there at an angle. It's not in the x or the y. So what we're going to have to do is break F2 into a force which is partly downwards, called F2y, and partly to the left, F2x. That is, it's the same as saying the x and y components. I'm just drawing it a little differently. Okay. Once we have F2x and F2y, we can pretend like F2 doesn't exist anymore, and instead we have these other two forces, F2x and F2y. So let's calculate them. What is F2x? Well, let's look. Here's F2. Here's the triangle. Here's the x side. Here's the y side. If I want the x side, that's the angle of 30 degrees. The x side is the side adjacent to the angle, so it's cosine. So it's going to be 20 cosine 30. And I know F2 is pointing down and to the left, so he's negative in the x direction because of the leftwardsness. So we get negative 17.32. We also need F2y. The y component of F2, well, the y side is the side opposite to the angle. Opposite goes with sine, so he's 20 sine 30. Is he positive or negative? F2 points down and to the left. Downwards means the y piece is negative. So he's equal to negative 10. All right, so now what I can do is I could pretend that F2 isn't there anymore. So I erase F2. And instead what I have is a F2x pointing to the left and an F2y pointing down. Okay? Because that's what F2 did. F2 gave two pieces of force. Some amount to the left and some amount downwards. And now we can see all of my forces are x and y forces on my picture. That's really pretty. That's going to make it very easy to plug stuff into my equations. At this point, we're done setting up all of our problem. Now we can start to solve. What's the question? Calculate the acceleration of my block. Okay, well, which direction is my block going to move? It's going to move in the x direction. It's going to slide along the table. So I'm going to look in the x direction, and I'm going to say all the forces in the x direction equals ma. Now I plug my numbers in. Let's look at all the x forces. I've got F1 to the right, so that's 100. I've got F2x to the left, so that's minus 17.32. And then I've got frictional force to the left, so that's minus frictional force. And from my picture, that's all the x forces. So, set it equal to ma, 10 times a. And now, of course, I'd love to solve for a, but frictional force is unknown to me. I don't know what this number is, and I can't solve two unknowns in a single equation. So what I'm going to have to do is come over here and try to figure out what's frictional force. So let's see, frictional force I know is mu times the normal force. Okay, well, mu, that was given at the top, that's 0.2. And now I need normal force. but I don't know what the number for normal force is, so we're going to have to solve this. How can I solve normal force? Well, look at the picture. Normal force is sitting right here. That's a y force. So let me use the y direction and say in the y direction, let's do F equals ma. What are all my y forces? Well, I've got normal force up. I've got gravity down, so mg is down. And I've got F2y is down, so minus 10. And those are all the y forces on my picture. I set that equal to ma, so 10 times the acceleration in the y direction. Remember, in this other equation, this acceleration over here was the x directional acceleration, which is what I'm trying to find. In this y equation, it's the y directional acceleration. But let's use our intuition. Will my block move up and down? No, there's no reason my block should be moving up and down. In fact, it's sitting on a table, so it's likely not going to move up and down. That means in the y direction, our acceleration should be 0. So all of this is just equal to 0. Now let's look at this equation. Normal force minus m, which is 10, times g, 9.8, minus 10 equals 0. And this I want to solve for normal force. So n equals 98 plus 10, which is 108. I now know the number for normal force. Good. What do I do with it? I go back to my friction and say mu 0.2 times normal force, 108. Then I get my calculator and do 0.2 times 108 and I get 21.6 newtons for friction. All right, good. So all of that allowed me to calculate what should the number for friction be. So I go back to the original equation I'm trying to solve, and I say 100 minus 17.32 minus friction, which I just found to be 21.6, equals 10 times A. So I get out my calculator again. I say 100 minus 17.32 minus 21.6, all of that divided by 10, because I divide the 10 over, and I get that the acceleration is equal to 6.1 meters per second squared. And there we go. Again, very similar to this first example. We're given a block, some series of forces on the block, and there's friction. I want to calculate the acceleration. How did I go about it? I started over here in the red box. I said, I know my block will move in the x direction, so I do the sum of the forces in the x direction. What are all my x forces? I look at my picture. In this case, all the forces were all x and y, so I didn't have to do any components. That's easy. That makes it easy. So I said, okay, I've got 100 force moving to the right, so that's plus 100. And I've got friction moving to the left, so that's minus friction. Those are all the x forces, set it equal to mass times acceleration. But then I'm stuck. I'm stuck because I don't know what this number of frictional force is. So I move over to the right side, the green box. What's my frictional force? Frictional force is mu times normal force. In the problem, I'm told mu is 0.2, but I don't know normal force. So I say, okay, how can I calculate the normal force? I look at my diagram of all the forces. I say, here the normal force is a y force. So in order to calculate it, let me do F equals ma, but do it in the y direction. So F equals ma for y. What are all my y forces? I've got mg pointing down, so minus mg. And I've got normal force pointing up, so plus n. And those are all the y forces. Set that equal to mass times acceleration. But I know in the y direction for this problem, my block won't accelerate. It's not moving up and down. So my y acceleration is just 10. So I solve for, sorry, my y acceleration is just 0. What am I saying? So I solve for n. I bring the mg to the other side. In this case, normal force is equal to mg, which is 98. Now that I know normal force, I go back to friction, and I say, okay, friction was 0.2 times normal force, so 0.2 times 9.8, which is 19.6. Finally, now I have friction. I go back to my red box, which is where my actual problem was. Now I can plug my number for friction. And then I go tick, 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 down and find my acceleration. Here, same exact process. I did it in a little more detail with the forces because we had a force here that's at an angle. And I wanted to show you if you have an angled force, but you want everything in x and y, you first find the components, which is this green stuff here, finding the components of the force. And then you could replace that angled force with your two component forces. So instead of having this F2 pointing at an angle, I instead have an F2x pointing to the left and an F2y pointing downwards. And now looking at our free body diagram, all the forces are x and y. I can now begin my problem. Again, I ask my question. I'm looking for the acceleration of the block. Which way will the block move? It'll slide along the table. So that's an x force, an x acceleration. So I do F equals ma in x direction. What are all my x forces? F1 is pointing to the right, so plus 100. F2x points to the left, so minus 17.32. And friction points to the left, so minus frictional force. Those are all my x forces set equal to mass times acceleration. I'm stuck because, again, I don't know frictional force, so I have to calculate it. So I move on to the bottom over here, and I do frictional force as mu times normal force. But again, I'm stuck because I don't know normal force. So I look back at my picture. Well, which direction does the normal force point? Points in the y direction. So I use F equals ma in the y direction to calculate normal force. What are all my y forces? Normal force is pointing up, gravity is pointing down, and F2y is pointing down. So those are my three y forces, set equal to mass times acceleration in the y direction. And since, again, the block won't move in the y direction here, the y acceleration is 0. Calculate normal force. Once I have normal force, plug it into my frictional force equation. Now I have frictional force. Once I have that, I'm golden. Go back to my original equation, plug in that number for friction, and now you have your acceleration. All right, let me do one more example. I've done two that are in the horizontal direction, so of course, let me do something a little different. Let's say this time what we have is a wall with a block on a wall. Maybe it's a box, and someone is pushing on the block with a force of, let's say, 50 newtons. The mass of the block is 10. Let's say this force is at an angle of 30 degrees like this. Given that the coefficient of friction between the wall and the box is 0.1, I'd like to calculate the acceleration. Okay. So I'm going to do like the last problem. I'm going to make a little free body diagram just because I think it might be helpful. So what are all my forces? So here's the box, let's say. Now, in actuality, when we do free body diagrams, this is how you're supposed to do it. Over here, I drew the box. Technically, I'm not supposed to draw the box. I'm supposed to represent the box as a dot. It doesn't matter, but physicists think the dot just makes the diagram look cleaner. Because what if the object is like a car or a plane? Then you have to draw a plane, and that's hard to do. And so we're lazy, so we just draw a dot. So here's my box. Now I have to figure out what are all the forces acting on this box. Well, let's see. Of course, we have my applied force, F, like this. What else? Gravity. Gravity is in here. So there's some force due to gravity. Notice if I'm pushing on my box like this, up and to the right, I'm kind of pushing the box up against the wall. But my box doesn't flow through the wall. It's stuck to the wall. It can't be pushed into the wall. That means there must be a force preventing my box from being pushed into the wall. That force, of course, is the normal force. Normal, remember, is perpendicular. This time our surface is a vertical surface, so a normal force would be horizontal, trying to stop you from going into the wall. So there's a normal force here, but this time the normal force happens to point to the right. Because I'm trying to push my box into the wall, to the left, so the wall is pushing back to the right, trying to stop me. Okay, are there any other forces? Sure, there's one more force. There's friction. Because of the little mu is 0.1 on my diagram. So which way will friction flow? Well, first figure out, if there's no friction, which way will my box slide? Is it going to slide up or is it going to slide down? Well, let's see. Gravity, if you remember, gravity is m times g, which is 10 times 9.8 for this problem, which is 98. So that means there's 98 newtons of force pulling me downwards. What's the force that's pushing me up? Well, it's some piece of this F over here, F being 50, so some smaller part of 50 is pushing up. I don't know exactly how much because I haven't done the components yet, but I know it's got to be something less than 50. So I've got 98 pulling down on the box, and I've got something less than 50 pushing up. Well, obviously, by logic, the 98 pulling down is bigger, so that means gravity wins. My box is trying to slide downwards. Since my box is trying to slide downwards, friction opposes that, so friction must be up. Obviously, if my applied force was 500, then likely the applied force pushing up is bigger than gravity, so my box would be sliding up the wall. If it's sliding up the wall, then friction would be pointing downwards instead. It always opposes the motion. So here we had an example where we couldn't really tell necessarily by looking at the picture. So we had to do a little bit of analysis and say how much is gravity? In this case, it's 10 times 9.8. How much is pushing up? Some amount less than 50. So the 98 is going to win. That means box is moving down, so friction must be pushing up. All right, good. So there's my free body diagram. I know my box wants to move in the y direction, so I'm going to want all x and y forces. However, I got an F sitting there that's at an angle. I don't like the angle in this case. So let me do components. I need an Fx and I need an Fy. All right, Fx. Let's look at my little triangle here. Here's the x side, here's the y side. The x side is the side opposite to my angle, so that means sine. So 50 sine 30. Is that negative or positive? Well, the force F is pushing up and to the left, so for the x part, it's leftwards, which is negative. So we get negative 25. Now we look at y. The y side is the side adjacent to my angle. Adjacent means cosine, so it's 50 cosine 30. Is he positive or negative? F is pointing up and to the left, so in the y direction he's pointing up. Up is positive, so he's positive. So plugging this into my calculator, I get positive 43.3. Now that I have this, I could say, let's get rid of this little F sitting here that's at an angle, because angles are bad, and let's replace it with two forces, one that points to the left of 25, and one that points up of 43. All right, so now we have our picture ready. All the forces are all set up, X and Y forces, just like we need them. And now we can answer the question. Question says, what's the acceleration of my block? Well, which direction does my block want to move? It wants to move in the Y direction. So I'm going to look in the Y direction, and I say, sum of the forces in Y is MA. What are all my Y forces? Let's see, I've got minus mg, that's the gravity pointing down. I've got 43.3 up, so plus 43.3. And I've got friction up, so plus friction. Those are all the y forces, set it equal to mass times acceleration. But again, I know m, that's 10, g is 9.8, but I don't know ff, I don't know friction. So we move back. Let's try to calculate friction. Friction is mu times normal force. Mu for this problem is 0.1, but I don't know normal force. Let's calculate it. Which direction is the normal force in? It's in the x direction. So let's look in the x direction, and I do F equals ma for x. X forces, I've got 25 to the left, so negative 25. And I've got normal force to the right, so plus n. Those are all the x forces. Set it equal to ma. So 10 times the x directional acceleration. Well, how fast will this block move in the x direction? Well, of course, we know the block is not moving through the wall, so it's not moving in the x direction. Thus, the acceleration in the x direction is just 0. So that's just 0. Thus, I could solve this for n. N is equal to 25. I now know normal force, 25. So I take that, plug it in up here for my frictional force equation. 0.1 times 25 is 2.5. I now know friction. Now, go back to my equation. Minus 10 times 9.8 plus 43.3 plus 25, I'm sorry, 2.5, the friction, not the normal force, is equal to 10 times A. So again, I get out my calculator, and I say 43.3 plus 2.5 minus 98 divided by 10 tells me acceleration is negative 5.22. I got a negative acceleration. Is that okay? Sure, it's okay. All it means is my block moves down. Of course it moves down. I said it was going to move down. Gravity is pulling it down harder than I'm pushing up. Even though friction is there, friction doesn't make it move in the opposite direction. All it does is slow it down from what it would have been. So there you go. Again, if you look at this as a general overview compared to these other two examples, you see we're always doing the same types of steps. You think about the question, you do a free body diagram, you show what are all the forces. If you have forces that are in the wrong directions, so in other words, if you want X and Y stuff, but you have angles, then you do components. Of course, the same can be said if you had a problem where you're on a ramp. Well, now you want parallel and perpendicular stuff, so if you have X and Y stuff, you do components for those. You do your components, and then you put them on your free body diagram. So now all the forces are in the right directions. Once you have that, you say, if I want to calculate the acceleration, how do I do it? Which direction is the acceleration, X or Y? Once you know then you do F equals ma in that direction. Plug in all the forces that are in that direction, set it equal to ma. If there's friction, you're probably going to have to calculate friction. So, use the friction equation. Frictional force is mu times normal force. How do you calculate normal force? The same thing. Which direction does normal force point? Use that direction, F equals ma, to calculate normal force. Likely what's going to happen, just every time, is the ma part is always going to be 0. Because if you're on a surface, you can't move through that surface. So the acceleration that's in that direction will always be 0. Solve for normal force, plug that into frictional force equation. You now have frictional force, plug that back into your original F equals ma, and you have your acceleration. So certainly more steps than we had to do before friction, but the steps aren't that bad. Look at this little bitty equation here and little bitty equation here. Yes, it took more time, and you had to do more calculations, but these are little baby equations, nothing to worry about. If you practice these enough, it'll become second nature to you. Each little step won't be anything hard for you or complicated. You just get through them, plug them into your main equation, and there you go. So this is how we're going to worry about friction. Any problem we've done with Newton's laws thus far can involve friction. I've shown a few examples. I haven't shown an example with ramps yet, but try an example with a ramp. Try an example where you have an inclined plane at 30 degrees. There's a block on a plane, 10 kilograms, and there's some friction, 0.1. Calculate the acceleration of this. Just as a quick overview, what would you do? Well, let's look at the free body diagram. What are the forces? mg is straight down. There's a normal force. The normal force always points perpendicular. So the normal force is going to point like this. Which way, up or down? Well, obviously, your block can't go through the ramp, so it must push off the ramp, which is that way. So there's a force like that. Normal force. Friction. There's also friction. Which direction will friction make this block or point? Well, I know my block wants to slide down the ramp this way, which is a parallel direction. So friction must stop it by pointing in the other direction. So friction points that way. So now I have all my forces. What are the important directions here? The important directions are the parallel direction and the perpendicular direction. This guy here is perpendicular. This guy here is parallel. mg is y. That's bad. Just like in this problem over here, our f was in this angled direction, which was bad, so we had to do components. mg here is a y direction, which is bad for this problem. So we're going to have to take mg, the gravitational force, and get a parallel piece and a perpendicular piece, which we saw that how to do previously. You know, you have the block, mg, there's a perpendicular side and a parallel side. This angle here is the same as this angle here. So here's parallel, here's perpendicular, and you do your little components, and you get components. Once you have them, then you could replace this mg with some amount of fg this way and some amount of fg that way. Parallel and perpendicular pieces. Okay, just like we did here, where our f got broken into an x piece and a y piece, and we got rid of him, replace it with the 25 and the 43 like that. Here we replace this mg with the perpendicular piece perpendicular and a parallel piece here, parallel. Once you have this, you now have your free body diagram done. Remember, you're thinking only about parallel and perpendicular. So you say, which direction will this block move? Parallel. So looking in a parallel direction, sum of the forces equals ma for parallel. How many parallel forces do you have? Here's 1, here's 2. So there they are, equals ma. You don't know frictional force. So you do frictional force, mu times normal force. How do I calculate normal force? Well, which direction is normal force? Here he is, perpendicular. So perpendicular, F equals ma. What are all my perpendicular forces? Well, I've got normal force and Fg, perpendicular piece. And da, da, da. So same thing, the same thing, except here we're looking at x and y. Here we're looking at parallel and perpendicular. Don't let the fact that it's not x and y directions make you think this is a harder problem. It's not a harder problem. Just in your mind, instead of asking questions about x direction and y direction, ask parallel direction and perpendicular direction. And you're doing exactly the same steps. Now, obviously, we've had some practice problems posted on Canvas for a while with the solutions. And I know there are problems with the inclined plane and friction, so be sure to look over them. But we now have all of the material we need for this first exam coming up. So I will be posting a video with an exam review, what to expect. I believe our exam will probably be for Thursday, but Thursday or Friday. Probably Thursday is when the exam will start. I'll post an exam review where I'll give a whole lot more information about it. But just be prepared for Thursday to have your test. We won't have any new material before then. So from now till the test is basically reviewing, going over all of our homework assignments, going over the practice problems that have been posted. And if you do that, then this first exam should be no problem for you. So I hope this frictional stuff made sense. As always, if you have questions for me about this, please email me and I'll be happy to go through it as much as I can with you. Also, be on the lookout for practice problems and the solutions, and also the video for our upcoming exam review. And until then, good luck.